Well, welcome to our second stat seminar. And today, well, just a couple of housekeeping things here. The session is being recorded. I know some of you have asked about that, and I believe that will be available. That Georgetown will send out a link to the recording. And then also, if you have questions, use the Q&A, which I think is available now. Okay, so let me get started. Today we want to talk about regression models. And first I want to talk about what's known as general linear models, or GLM. And then I'm going to talk about generalized linear models. And then I want to look at some model building methods, those both old and new, or newer. And then I want to use a study that I did a little while ago comparing nested models. And then we'll also, in the process, talk about model validation. So when you talk about linear regression, we mean that our outcome, our dependent variable, is continuous and it's normally distributed. And I have the sort of well-known formula there for linear regression, where you have the outcome, which we designate as y, and it's equal to some regression coefficients, the b sub 0 being the intercept or the constant, and then the b sub 1, b sub 2, and so on are the regression coefficients for the corresponding independent variables that we're looking at, which I've designated as x's. And so the way that we interpret the regression coefficients are the change in y, in the outcome for every unit change in the independent variable. And the particular statistic that we're interested in linear regression is r squared. And that's defined as the proportion of variance in y accounted for by the independent variables. And then the other important thing that we'll look at in linear regression is residuals, which is the predicted value minus the observed value. And the residuals need to be normally distributed with a mean of 0. The data itself doesn't need to be exactly normally distributed. It can, actually vary quite a bit from being normally distributed data and be okay. But if the residuals are not normally distributed, then we need to go back and rethink our model. So let me illustrate this with a picture here. And so we're looking at as our dependent variable cholesterol values, and our independent variable is age. And so I have the individual data represented by circles here. And then the diagonal line is the regression line that best fits these. And so I want to look at the way that we calculate the regression. And so the horizontal line will designate by capital Y, and that's the mean cholesterol level in our sample. And so the question we're asking is, if we want to find out or we want to predict the value of cholesterol in any given sample, then without any other information, then the best predicted value is the mean. But what we're asking when we regress, do a regression, is does the addition of another variable add to our ability to predict values? And so if we add age to our equation here, then we want to see is how well age predicts cholesterol over and above the mean. And so we'll take a particular individual here, and we'll call their value y sub I, I for the individual. And then we have the predicted value based on the regression, and so that's what we'll call y prime. And so we have three values there, the mean of cholesterol, the observed value given a particular age, and then the predicted value given a particular age, which for this patient looks to be about 54 or so. So we can then take the total distance from the observed to the mean, and we can partition that or separate that into two different components. One is the distance from the predicted value to the mean, and then the other one is the distance from the observed to the predicted value, okay? And so this can be represented by what we call a sum of squares. And the reason we square it is because if you didn't, then everything would end up being zero. But so the distance from the observed to the mean, y minus y, or y sub I minus y. And then the two partitions, the predicted minus the mean and the observed minus the predicted. And so what we have then is a sum of squares for the total distance between the observed and the mean, and the sum of squares for regression, that's the difference between the predicted and the mean, and then the error, which is the difference between the observed and the predicted value. So it turns out then that we can sort of represent this in words by the total sum of squares is equal to the regression sum of squares plus the error sum of squares. And the R squared, the value that we mentioned, is the total variance accounted for by the total variance in this case, cholesterol accounted for by age. And so that's the sum of squares regression divided by the sum of squares regression plus the sum of squares error. And if we take the square root of R squared, then we get the correlation, we get the absolute value. The correlation could be negative or positive, depending on the slope of the line. In this case, it's a positive, but if it was, going the other way, then we would have a negative correlation. So this is what we mean by what we do when we do regression, linear regression. And so the important thing about linear regression is the distribution of the residuals. That's the difference between the observed and the predicted values. And so we can do what's called a QQ plot, quantile to quantile plot, or normal quantile plot, and we can see if our residuals line up on the normal line there. And if we do, we're in good shape. If they deviate from that, then we need to go back to the drawing board. And so another check on this is to look at the residuals and how they're distributed according to our independent variable. And so what we should see is something like this, where the sort of scatter is from zero is more or less, random. On the other hand, if we have plot our residuals against age, then if we get something like this, then we don't have normally distributed residuals. And you can see that as age increases, the difference between the observed and predicted values becomes quite large. So again, then we'd have to go back and do something else to correct this. Okay, and then this is the just a picture of what you normally see, the plot of the individual observed values, the regression line, and its 95% confidence interval. So the example I gave was just an example of simple linear regression, but we can do multiple linear regression where we have any number of independent variables. And these variables can be continuous, they can be dichotomous, they can be categorical. And so the regression coefficients, the B, That represents the rate of change in Y for every unit increase or decrease if it's a negative in X1 or X2, X3, so whether. But the thing to remember here in multiple linear regression is that they're adjusted for all other X's or all other independent variables in the model. So for example, if we had cholesterol as a function of age and weight, then we would have 2 regression coefficients plus the intercept, the B sub 0. And so each regression coefficient would be adjusted for the other variable in the model. Okay, then when we talk about generalized linear models, we're addressing the situation where we have something other than normally distributed data. And the most common one that you'll see is binary logistic regression, where the outcome is dichotomous, dead, alive, yes, no, positive, negative. And so we can calculate the odds of the outcome, which is the probability of the outcome divided by 1 minus the probability. And so if we take the natural log of the odds, then we have logistic regression, which has, except for the left-hand side of the equation, is pretty much the same ideas in linear regression, where we have regression coefficients for each independent variable in the equation. And so the way that we interpret this is that is a change in the log odds of an event with 1 unit change in the independent variable. It could be linearly decreasing or increasing. And so I didn't have a picture of it, but I'm sure everybody is familiar with the bell-shaped curve. So for a normal distribution, this is the curve for logistic regression. And you might say, well, that doesn't look, very linear to me. Well, it isn't at the extremes, but right through the middle here, it is linear. And as we'll see later on, I'll give an example. If we're into the extremes of the distribution here, then we might be in trouble. Okay, so when we look at the regression coefficients, the B or the beta here, the slope coefficient is the rate of change in the log odds of the event as the independent variable changes by 1 unit. And so one of the things, of course, we want to know, probably rather than the log odds, is the probability. And so we can calculate the probability by exponentiating our regression equation. So the probability of our outcome given an independent variable is just the regression equation exponentiated and divided by 1 plus the exponentiated regression equation. And that gives us the probability of the event that we're interested in. So I have an example here. And so I'm, in this case, regressing cardiovascular death with age. And so this is my output from my program that does this. And so I have the regression coefficient for age and then the constant, the B or the beta sub 0. And so I can get the probability of cardiovascular death given a particular age by solving the equations that I illustrated there, how you would, plug in the equation for that. So you'd have the constant plus the regression coefficient times whatever age you're interested in, and then dividing that by 1 plus that exponentiated regression equation would give you the probability of a cardiovascular death. So in this slide, what I've done is I've changed the output from getting the regression coefficient to actually getting the odds ratio. And so the odds ratio is found by exponentiating the regression coefficient. So in this case, we get our odds ratio of 1.1, and then the confidence interval, the 95% confidence interval for that odds ratio. And as you know what we're looking for is a confidence interval that does not include 1, because if the odds ratio is 1, that means there's no difference in the odds between whatever, say, groups you're looking at, or whatever age, whatever other independent variable you're interested in. And so the way that we interpret an odds ratio in this case would be for every 1 year increase in age, the odds of cardiovascular death increases by a factor of 1.1. Or another way of saying that, there's a 10% increase in the odds of cardiovascular death for every 1 year increase in age. So we can, as in linear regression, we can also do multivariable logistic regression, where we have more than one independent variable. And just as in linear regression, the regression coefficients, the betas in this case, are adjusted for all of the other variables in the equation. And so it's interpreted in the same way as we mentioned earlier, that the increase in the beta coefficient is increase in log odds for a 1 unit increase in X with all the other held constant. Okay. So in evaluating logistic regression models, there are 2 statistics that we want to look at, discrimination and calibration. In the linear model, what we're primarily interested in looking at the R squared and how large that is. But in logistic regression, discrimination is indexed or is assessed by what we call the C index, or it's the same thing as the area under a receiver operating characteristic curve. And I have a little picture out of it here, where the diagonal dotted line, if your discrimination index is 0.5, which would correspond to that line, then you have actually no discrimination. It's just a coin flip as to whether you can discriminate between a person who experiences the event or a person who doesn't. If the area under the curve, or the C index, is greater than 0.8, we usually call that good discrimination, really good discrimination. Between 0.6 and 0.7, I would call that kind of mediocre, sort of okay, but average discrimination. Although I have seen articles where they call like 0.65 really good discrimination, but that's kind of overstating your case. The other one statistic that we're interested in is calibration, where we're interested in looking at the predicted probabilities and the observed probabilities, and whether they're equal or not. And so what we do to take a look at this is we calculate the slope of the predicted probabilities and the observed probabilities. And obviously what we're hoping for, or ideally, would be a slope of 1, that would, meaning that they were equal. So here's some ways that you will see calibration. It might be done by bar graphs, where the horizontal axis are quintiles, or most often deciles, of the predicted probability, and then the vertical axis is the observed probabilities for each of the bins of the predicted probability. Another way that's oftentimes presented, and which is maybe a little more clear, is by actually plotting the lines. And so the red dotted line here is my ideal calibration, where I have a slope of 1, and then my observed or actual calibration slope in this case is 0.97. So I have really good calibration here, since I observed slope is pretty close to a slope of 1. So one other thing in logistic regression that you need to be aware of is extreme values in evaluating your model. And so I've highlighted some here some of the coefficients or the odds ratios and confidence intervals in a logistic regression. And so what you see here with the one with intervention at 2 years, the odds ratio is 0.01, and you can see that the lower bound is getting pretty close to 0. On the other hand, the one for females, you can see that the upper bound is really huge. So, we have some issue here. And then the other ones that I have highlighted here, you can see that both the odds ratios and the confidence intervals are very, very small, very close to 0. So what these would indicate is that we're perhaps in the sort of the extremes of our logistic regression curve that we looked at earlier. So if you see these kinds of odds ratios and confidence intervals reported, you need to have some question or be a little skeptical of the validity of them. Okay, one other thing that I want to mention in terms of generalized linear regression is what's known as Poisson regression. And here our outcome is a count over some unit of time. So for example, we may have ICU infections per month or non-fatal cardiovascular events per year. And in a normal distribution is described by its mean and standard deviation. In a Poisson distribution, it's described by its mean, but the mean and variance are equal in a Poisson regression. And if the variance is actually greater than the mean, then we call that over-dispersed. If it's less than the mean, then we call it under-dispersed. And if this is the case, which is most often, most data that I have seen in medical research is usually over-dispersed, then we can use another regression method called negative binomial regression if our distribution is over or under-dispersed, because it corrects for that over or under dispersion. Okay, then I want to get into how we develop multivariable regression models, whether it's a linear model or a logistic model or any other kind of model for that matter. And so typically what you do first is develop the model, and we call this your training data. And you'll see this in the literature a lot, where they take a certain percentage of your data, develop your model, and then they'll use the remaining portion of the data to test their model to see how valid it is on another part of your sample. And then a third step, which you may or may not see, is to validate the model. And so sometimes they might divide their data into 3 parts to do those 3, but typically the validation should be done on a different sample. In other words, you would get your model from your training data. You would test that on you might test that on part of your data that you've held out to test your model, and then you would, once you get the model a valid and reliable model, then you want to test that on your validation data, which ideally is a different sample. But it's very rare that you see it tested on a different sample, because usually you don't have that available to you. So the other aspect of developing models that we want to talk about is how many predictors, how many independent variables can you have in your regression equation? And then going back to last month's seminar, we want to talk about the role of p-values in developing models. And then I want to look at older methods versus newer methods. So probably the most common method that you'll see for developing a model is what's known as stepwise regression. And there's two kinds of those, forward selection or backward elimination. So with forward selection, you start with an empty model and then you add variables to it. Backward elimination, you start with all the variables you have in your model and eliminate them one by one. Then another method that actually I still have seen in recent literature is where you take all variables that are significant, statistically significant in univariate analysis, and then you put those variables into your multivariable model. Okay, that is the worst method that there is on the planet, so don't do that. Another way that I've seen this done and is still used in the literature is that you include all of the variables in your initial model, and then you take out or exclude those that are not significant. I'd probably refer to that as the second worst method. The method that I want to talk about primarily today is what we call penalized regression or regularized regression. So in stepwise regression, as I mentioned, we do either forward selection or backward elimination. And so there's an alpha error rate for inclusion or elimination. And as we talked about, this is the p-value. As we talked about last time, that p-value is arbitrary. Not only that, when you do stepwise regression, you run into the problem multiplicity. That is, you're starting to do a lot of tests. And so as you do that, the alpha error rate becomes inflated. And sometimes in stepwise regression, you'll see that the p-value chosen is not 0.05, but sometimes it's 0.1 or even 0.15. And they do that, and the argument is that we don't want to miss any important variables. But again, that has the issues of it, of the p-value being arbitrary. And then if you have a lot of variables, then you start to inflate the alpha error rate. Now, if you have a small number of variables for your model, then a stepwise regression is probably okay. If you do stepwise regression, I think that the recommendation for most statisticians is that you do backward elimination rather than forward selection. And you say, well, shouldn't you get the same result? Well, a lot of times you do, but not necessarily will you get the same result using backward or forward selection. And then the important thing to remember about doing the sort of ordinary regression here is that you need more cases than you have variables. And sort of the rule of thumb that you'll see is anywhere from 10 to 20 patients per variable. Or if you're doing logistic regression, then you want 10 to 20 cases or outcomes per variable. So, so if you have, say, 5 variables that you want to look at, then at the extreme, you would need about 100, patients or subjects in your analysis. Okay, so what I want to focus on is actually a better way of doing regression and selecting variables that go into the model, and this is penalized regression. And what penalized regression does is it shrinks the regression coefficients towards 0 by applying a penalty on their size. And this penalty, we vary that in the analysis, and the best penalty, so to speak, is selected by cross-validation. That is, we do a number of analyses where we take a certain percentage of the data, and then we develop a model, and then we cross-validate it on the remaining part. And basically what we're interested in doing here is minimizing our residual sum of squares. So the thing about penalized regression, which is sort of interesting and kind of neat, is that you can accommodate a large number of variables. And in fact, the number of variables can be greater than your sample size. So that's what I mean by P being the number of variables and N being the sample size, that P can actually be greater or larger than your sample size. And the penalties, you don't really need to remember this. I just want to point this out for completeness here, is that the penalties that are applied, there's two kinds, an L1 and L2 penalty. That's our shrinkage parameter. And there's two different, well, actually there's more than that, but the primary ones that are used are what we call ridge regression, where our penalty is the squared of the regression coefficients, and S here refers to our shrinkage parameter. The lasso, or the least absolute shrinkage and selection operator, the formula actually looks the same, but the penalty is slightly different. The penalty is the absolute value of the regression coefficient being less than some shrinkage parameter. And then a number of software packages do what's called the elastic net. And that is that you can vary between the ridge regression penalty and the lasso penalty. And typically the way that this is set up is ridge regression is, if you want to do ridge regression in the software, you code it as 0. And if you want to do lasso, it's coded as 1. But many software packages allow you to vary that shrinkage parameter between 0 and 1. And that's what's referred to as the elastic net method. Okay, so what I would like to do in the remaining time that I have is take a particular, a real life example here that I did a while ago, where we want to predict atrial fibrillation in hypertrophic cardiomyopathy patients. And so our atrial fibrillation, of course, is a yes or no. So they either experience the event or they don't. And so in our data set that I'm going to analyze here, we have 92 events out of 2,600 and some total patients. And we have 48 potential predictors that we want to look at. There are demographic variables, clinical history, there's morphology, gene mutation, there's imaging data, and there's biomarker data. And so we have a fair amount, quite a large amount of potential predictors that we're looking at, or independent variables here that we're looking at. And so I do this not for you to sort of read through this and check out all the numbers, but just to show you the large number of variables that we're going to initially include in our penalized regression here. And the table I have here is actually from the paper that actually is under review now. And I should point out that the analysis here is going to be a logistic regression. Obviously, that's not the actual analysis we did, because there is a time element from their entry into the study to when they experience the event, or their last follow-up if they don't experience the event. So that is actually what we're going to talk about next month, is time to event data. But just for illustration here, I'm going to just do simple logistic, well, I guess it's not entirely simple, but a logistic regression analysis. And so if I set this up and I'm using Stata to do the lasso, you can see it's fairly easy to set up. And so I need to tell it what kind of data I have. So it's a logid, it's logistic data. And then my outcome, which is the afibrillation event, and then my list of variables here. And let me say that variables that have numbers in them here in front of them are because there was a fair amount of missing data. So we imputed missing data, and the numbers refer to an imputation set that we did. We actually did 10 different imputed sets. But anyway, so you can see we have all of our variables here. The ones I've highlighted are imaging variables, which was sort of one of the primary groups of variables that we were particularly interested in. And then I've set a seed number here, which if I want to repeat this and get the same results, then I can do it by setting the R seed to a particular number, the random seed. If you don't do this, then you'll never know. You'll probably never be able to repeat your results again. Okay, so this is how it's set up to run. And so if I run it, then my output, again, is fairly straightforward here. So you can see that in my description here, I have a first lambda, lambda before, the selected lambda, lambda after, and the last lambda. Okay, now lambda is my shrinkage parameter that's being varied. And then the one that it stars, or the one that it's selected, selects this on the basis of the smallest cross-validation deviance. So in other words, this has the smallest error in it. And so what I see from this particular table here is that the lambda that it's selected has 10 non-zero coefficients in it. And you can see that the last lambda here, there's actually 13 that show up, but the best model is one with 10 of my variables in the model. Okay, and so I can look at how the variables and the order in which they were selected, and so you can see that in this case, the two variables that were selected with non-zero coefficients were left atrial volume and contractile percent. And then the third one that was selected was reservoir percent, then age, then BMI, and dyspnea were selected. And then on down to the 10th variable, which again here is my smallest cross-validation deviance. And so, and there's a couple more non-zero coefficients, but what this is telling me is that my best model would be one with 10 variables in it. And so these are the ones that are selected: age, BMI, the New York Heart Association categories, dyspnea, which is yes or no, a history of arrhythmia, which is yes or no, then left ventricular EDV, left atrial reservoir percent, a history of AFib, LA volume, and LA contractile percent. So those are the ones that variables that have been selected. And so now what I want to do is I want to then take these 10 variables and I want to apply them to my data. Okay, and so I'm just going to run a regular logistic regression here with these 10 variables. And you can see that I have the typical output here for logistic regression, the odds ratio, the 95% confidence interval, a p-value for each. And then also a piece of information that is really important here that we're going to look at is the log likelihood. And this is a statistic that you get, that you use then to see if a reduced model is just as good as the model with 10 variables in it. And then up here, my likelihood ratio chi-square has 10 degrees of freedom, or the number of parameters that I have in my model. So what I'm interested in here is, well, okay, can I make the model simpler? Can I have a reduced model that is just as good as the model with the 10 variables in it? And so then how do I reduce the model? What variables do I select to take out? Well, you can see there's kind of, there'd be too large a number to do for every possible combination. But I can sort of look at this and I can get an idea. So what I might do, which you say is not the best thing to do, is I look at the p-values here. I could just take the ones that are statistically significant at p less than 0.05, which are age, LA volume, and contractile percent. And so I can see if that model is just as good as my model with 10 variables in it. So I do that, and here is the model with just the 3 variables in it, age, volume, and contractile percent. And you see that I have a different log likelihood value now. And so what I can do is calculate a chi-square test, which the chi-square is equal to -2 times the difference in log likelihoods. And so the 355.2 here, that's the one from my model with 10 variables in it. So if I do that computation, I get a chi-square value of 13.5. And it has 7 degrees of freedom, because you remember that I had 10 variables to start with, and now I have just 3. So that's, 10 minus 3 is 7 degrees of freedom. And so if I calculate the p-value for that, I get, 0.08. And what I'm looking for here is, well, first of all, the traditional kind of way of looking at it is you want a non-significant chi-square value, because that tells you then that you have a pretty good fit to your model. But more importantly than that, what I am interested in is looking at the chi-square value itself and the degrees of freedom. And ideally, those should be equal. And so in this case, you can see with just my 3 variables, they're not really that close, 13.5 versus 7. So I'm thinking that maybe this 3 variable model is not my best. So I can go through some other combinations, and I'm not going to bore you with, going through all of them, but this is the, I put back in reservoir percent and dyspnea. And so now you can see that, again, I have a likelihood ratio here minus 358 and some. So I'm going to calculate my chi-square -2 times the difference in log likelihoods, which in this case turns out to be 6.9. And then you notice that now I have 5 degrees of freedom because I've got 5 variables in my model. So I have 5 degrees of freedom with a chi-square value of 6.9. So now this, as it turns out, is as close as I can get the chi-square value and the degrees of freedom. And so this is the model that I'm going to choose as my best model. And what I want to point out here is that you can see that when you do each variable, the odds ratio of each variable, not all of them are less than 0.05. And so that's what you want to, I think, take away from this, is that the best model doesn't always have statistically significant values for the odds ratio, or if you're doing linear regression for the regression coefficients. And I've a number of times, had papers sent back with a comment, why are there non-significant variables in your model? And so I, try to gracefully explain that to the to the reviewers, that it's the prediction. The model is predicting based on all of the combination of the variables you have, not on any one in particular. So that's kind of going through examples is how you build a model, or how you might build a model using penalized regression. And then if you want to try and reduce your model to compare models that are smaller than your largest model and see if it's just as good as far as prediction. And as I mentioned, what you want is a chi-square value that's ideally, or that your chi-square value is equal to your degrees of freedom. So this is the model then that I'm going to do my discrimination and calibration with. And so you can see that my area under the curve here, my C index is 0.75, which is okay. It's not spectacular, but it's pretty good. So this means that I have pretty good discrimination between those who experience the event, in this case, afibrillation, and those who don't. Then the other thing I want to look at is the calibration. That is, how well are the observed probabilities line up with the predicted probabilities. And so in this case, you see I don't do quite so well here, because what I want is all of my points here to have a slope of 1, but my slope for the values that I got is 1.57. So I don't have very good calibration at all here. In other words, there's quite a difference between the observed and predicted values. And you can see that this is primarily occurring because of the largest value here for the predicted probability, that it's the predicted probability is in the 10th decile here, less than 0.08, but my observed probability is greater than 0.10, in fact, it's about 0.12. So there's a big difference there between my observed and predicted probability at the largest values there. So I have kind of a quandary here that I have okay discrimination, but my calibration is not real great. Okay, so this is my final model then that I'm going to accept here, that I'm going to use, and my discrimination index of 0.75, but my calibration index is quite a ways away from 1. Okay, so let me finish up here by talking about software that does the penalized regression. You can do it in SAS, GLM Select. I've done it in Stata because Stata is really easy to use. And Stata, I'm not sure about SAS because I haven't used that, but Stata, you can do lasso, you can do ridge regression, you can do elastic net. And the type of data that you can do it for is normally distributed data or linear regression, logistic regression, and then you can also do it for the Poisson regression. There's also a Stata add-on that's been developed by someone outside of the Stata Corporation that's called LassoPack. I've worked a little bit with that. Actually, a couple of us from Biostatistics are looking at at applying that particular package to a set of data. The one that actually, though, that I like the best is in R, GLMNet, where in addition to all the other things that you can do, it also, the type of data you can include is time to event data or Cox regression models. So that's, I think, a little bit more useful in terms of the types of data that you're able to do penalized regression on. So to conclude, just to summarize, if you do just ordinary regression, you have to have more subjects than you do variables. On penalized regression, though, that's not necessarily true. You can have a large number of variables, even more than the number of patients. And then for testing reduced models against a larger model, for linear regression, it's the R squared that we're interested in. the more variables you have in a linear regression, the larger the R-squared is going to be. So when you try to reduce your model or look for a more parsimonious model, you want to look at the decrease in R-squared. And, you know, if it's not very much, and actually there's a statistical test you can do for that as well. But if it's small, then your model is probably just, your reduced model is probably just as good. And then, as I've illustrated, we use the log likelihood for the logistic regression. And then Poisson regression also has the same sort of thing, a goodness of fit chi-square that we can use to test whether our reduced model is just as good as our larger model. So I have a few references here. Some of these are more easy to read than others, but they give you kind of a good idea of the different aspects of statistical modeling or regression models that you would probably ever want to use. So I want to thank you for this time, and I think that we have just a few minutes left, so let me see if I can deal with a question there. Oh, so is there a handout available? Well, actually, the session is being recorded, so you can there's not a handout I have, a paper handout, but you can view the slides themselves. Let's see, the second question says, when you said ideally validate on a different sample, well, okay, what I mean by that is that you have a sample that it's the same type of patients. So for example, if you have, say, colon cancer patients or coronary artery disease patients, they have to be the same set of patients, obviously, but it's a sample that's different, that's outside of the sample that you have. And so what you'll find is that there's very little, well, not very little, but often that your model won't generalize as good to a different sample, but what you're looking at is how good does your model work on a sample that's entirely different. But if I understand what you're getting at here, it has to be the same type of patients. Let's see, our Logit, Probit, and Tobit model is still in vogue. Yeah, they are, although primarily the Logit, Probit, and Tobit models you see more in basic science models. And then the question is also what about developing the theoretical model according to a rational hypothesis? And so sure, you want to base your model on what makes sense. So that's in last time in talking about p-values, that you need to base your decision on of a model on what is what's important clinically or rationally to look at. So yeah, you're definitely right about that, and in wanting to develop models that make sense. And I might also add to that often you want to develop a model, particularly with observational data, that you might want to include variables in there like age, sex, race, and leave them in the model no matter what they look like in terms of statistical significance or not. Okay, let's see. What about what about power analysis? There is a way of or there are methods for doing sample size and power analysis calculation. That's kind of beyond the scope of what I want to get into now, but there is, I'll see if I can find some references for that. They might be in some of the references that I have that I listed, but I'll try and check that out. And then another question is, can you elaborate on why it is a bad idea to first do univariate analysis? Right, that's exactly right. It's because non-significant variables in your univariate analysis can turn out to be important in the regression results. They also reverse can be true, although not quite as often, is that variables that are significant in univariate analysis turn out not to be important to your overall model. So that's generally why it's not a good idea to just take variables that are significant and put them in the model. Okay, let's see. I don't see any more questions right now, so I'll stop there. And if you do have more questions or have some other things you might like to discuss, you can email me at my MedStar address here, email address. So I want to thank you for your time and for participating in this particular seminar. As I mentioned, next month in December, we'll look at models for time to event data, where you have not only a dichotomous outcome, but then you have a time to that event and how that's analyzed. So again, thank you for your time, and hope to see you next month.